Hey everybody, I just wanted to make a short video here covering something. I was working on a little project between semesters, sort of along the lines of something I always try to impress my students, that game engines can be used for more than just making games. For example, one that I often try to impress on people is if your end goal is just like an animated video film sort of thing. Animations and sound are trivial in any game engine, which means that a game engine will be really easy to put together a animated video in. Or another one that we can have nice control over is things that we would normally think of putting in a PowerPoint slide deck, but put something together in a game engine. And you can do so much more with it. Make it really impressive really quickly, because it's kind of trivial compared to most of our big games that we would be thinking about making with that engine. The idea of polymorphism again. Tools can be used for more than their intended application, so obviously game engines are polymorphic to other things we might want to do. What I was working on in particular was just interfaces, graphical user interfaces for basic applications, only 3D. So like on a payroll calculator, it's like a cube, and you look at one side to enter information or access the database, and you spin the cube around, and then there's all the tax information, or spin it up to see the gross pay or hourly records. And a three-dimensional interface is what I was working on, just to see how that goes for regular applications, business sort of applications instead of games. I thought it might go good for VR. So to practice that, I look for a game engine in Java. That's my favorite language to code in. I'm working in a lot of different languages, but JMonkey stood out, so I started working in JMonkey, and as I was looking around, I kept seeing something that I'd seen over and over again throughout the years, and that's the note that whenever game developers need to use quaternions to describe the rotation of our three-dimensional object, it always says this is really hard math, but it should not be for a game developer. It's going to seem that way for sure, because, well, we usually don't see that till a high-level math class. First place I saw it was an abstract algebra class, and it's probably the same for most people as far as seeing it in a math class instead of a game development thing. And an abstract algebra class is going to be at least a 400 level math class, so it's way up there. And in those classes, you're learning all these theories, all these different things, but we don't really need all those. When you see quaternion, and well, I've never seen that in a math class, and go to look it up, try to look stuff up on it, you're going to see all that high-level theory stuff, and it's going to seem really confusing. But what game developers need from quaternions is really easy. It gives us unique rotation in space. I'm getting ready to write some stuff on the board, so just a quick preview of it. If we use angles, which you probably think of from like a flat surface, rotate so many degrees around, if we do that in more than one, if we do that in 3 dimensions, we need at least 2 angles, which means that there's more than one way to describe any rotation in space. Quaternions are the unique rotation. There's one and only one way to describe any direction. We're pointing that way, that way, that way. If we have multiple angles, there's several ways we could get to that pointing in that direction. But quaternions are unique. There's one and only one way to point in that direction. So I wanted to introduce quaternions, break it down to just the part that game developers need, because that rotation is actually kind of easy when we get to it, and it's built up from stuff that you have seen if you've gotten to at least an intermediate algebra course. So algebra 2 in high schools usually, or somewhere around there. Some people may see it as algebra 1 in high school. At the college level, it's usually intermediate algebra. If you've gotten to that level, you've seen the parts to build up that unique rotation, which is all game developers need. And then quaternions are a lot less confusing. I keep seeing that note, and I was like, well, I already have a lecture prepared for the game development classes I'm teaching this fall and again next spring. So why don't I just make it as a YouTube video and show how quaternions should simplify things for game developers, not make them harder. So let's get started in that. So the first step here is quick pointers about graphics, which if you're watching game development videos, hopefully you're familiar with graphing. Our 2D, we have the X and the Y axis, and we describe things as a point, such as a point here that's 3 units over and 4 units up. We describe that as the point 3, 4. Carries information about where it's at relative to the origin, but a better way to describe that, which again hopefully you're familiar with already if you're into game development, is instead of that point, the vector 3, 4, which is often easy to visualize, especially if we're working entirely in graphics, as the arrow that goes from the origin to that point. Because unlike the point, which is locked in place, we can move that arrow around. Start over here, and that arrow still encompasses the same information it does here. So that's the vector. It's the vector that points 3 horizontal units and 4 vertical units in 2-dimensional space. So I'm going to start with that, and we could describe it with an angle. In 2D, that works good with an angle, but as stated in the intro, with 3D we need 2 angles, and then we lose the uniqueness. There's more than one way to describe any direction like this in 3D space. So we need another way to describe that rotation. So let me erase back, and instead of plotting X and Y, let's think of another thing we could plot. Somewhere along the way, I drew the 3, 4, 5, 3, the 3, 4, because hopefully you remember 3, 4, 5 triangle. That way we have nice whole numbers to work with here. You may have encountered complex numbers, sometimes called imaginary. They represent real things. Imaginary is not quite the right term. It helps to think of it that way sometimes, but for example, it shows up all the time in electricity, and it really does hurt when it shocks you. So it's not really an imaginary thing. But complex numbers, which we can represent with a real part and an imaginary part. A plus BI is the way you may have seen it written in class, and our rule is I is the square root of -1, which means I squared is a real -1. Then we could describe our rotation this way instead of with angles. So we have a real part. I'm going to draw a real vector down here. Maybe I should do this in colors. Hopefully the colors will show up on the video. I'll try some green here. So we have this real part that is the vector, which I'll denote with angle brackets instead of parentheses, of 5 units horizontally and 0 units vertically, or 5 units real, 0 units imaginary. I guess that does fit nicely in sentences. But if we split it up and write it this way, that real and imaginary part, instead of X and Y, we could do is 3 plus 4I. Because if we come 3 units down the real axis and 4 units up the imaginary axis, we get this vector, which the real component of is essentially the same as that, right? We turn that into a right triangle, we get the Pythagorean theorem, where a squared plus b squared equals c squared, or in this case 3 squared plus 4 squared is going to give us 5. So that's an alternative way to describe rotations. You may not have seen that in your elementary algebra class, but hopefully that makes sense, and we just end up with this right triangle, and we're describing it as a vector pointing off in the real and complex axes instead of X and Y like we normally think about them. Hopefully that looks familiar. and the Pythagorean theorem, you remember that from elementary school or somewhere along the way. Oh, forgot a little 2 there. But it gives us another way to take this vector in space and rotate it instead of just angles. Which in 2D, it doesn't make any difference because we still have one way to describe any rotation all the way around, just like we only have one way to describe it with angles. But it makes a big difference when we get to 3D. So the first thing to notice is that this requires a plane, not a single axis. So we need 2 axes. So if we're in 3-dimensional space, I'll just do X, Y, Z this way. The normal math class way, most of our game engines alternate that in some manner or another. But in 3-dimensional space, we have 3 planes here, right? We have, if this will show up here, we have our X, Y plane. Then we have our Y, Z plane. Forgot my little Z label up here. Oh, I've got the Z label. But then we also have our XZ plane. So instead of 3 axes, in order to describe, if we wanted to describe rotations this way instead of angles, we would need 3 planes. And we can do it just from an extension of these. So we have the real and imaginary, which I'm going to change that to the X and I, because one of our standard notations. Then we have 2 other planes. We have the Y, and we normally use J as the standard mathematical notation for it, as well as Z and K is the mathematical notation we would normally use. So we take this concept of imaginary numbers and apply that on 3 planes, which actually add up and give us a 4th dimension, which is part of the reason quaternion seems so complicated, because we have 3 complex dimensions, and then those go together to give us the real dimension, which this is probably still seeming really complicated, and I need to write down some rules, kind of the equivalent of this. Like I is -1, so I squared, or I is the square root of -1, so I squared is -1, which you probably remember from your math class, if you've had at least intermediate algebra. So we continue that on. So with quaternions, I squared is J squared equals K squared, which gives us -1. So I, J, and K are all square roots of -1. We're just thinking about them on a different plane in 3-dimensional axes, which you'll notice. I'll use the word imaginary. Imaginary, 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 real. So we're actually dealing with 4-dimensional space, which is part of what makes it seem extra confusing. But I have a clarification point here in a moment, coming up in a moment, which will help to deal with that 4-dimensional space a little easier. And another thing about this is they are all unique. Back to that uniqueness thing, we get that because quaternions are non-commutative. The order that we multiply things in makes a difference. So I times J, right, these are both sort of like a square root of -1, get into details and all that complicated stuff from the high level math class. So quite think about them like that way, because that's not a real thing, right? So when we define the multiplication, I times j gives us a k. Then k times I gives us a j, and j times k will give us an I. So that's how we define the products of these three sort of imaginary numbers. I'll just use that word because that's what most people use in the intermediate algebra class, so that's the word you're probably familiar with. So we have that, but the thing is, order matters. This is where we get the uniqueness from. Order matters. So flip, that's supposed to be an L, flip to get negative. So I times j gives us k, but j times I would give us negative k. Would it be confusing if I wrote it this way? So if we multiply this way, we get k. If we multiply this way, we get negative k. That's probably confusing to write it that way, but flip the order to get the negative. Flipping the order gives us the negative. And that's where we get the uniqueness from, the non-commutative part. So that's the basic idea of the quaternion, as far as graphing goes and what we'll need to build something up. So we take these three planes and add them up together, and then each one of those, right? So these little planes that I drew on here, let's see, X usually goes with I, Y usually goes with J, and Z usually goes with K. So if we're in the XY plane, X times Y is I times J. So this is actually the K plane. Y times Z is J times K. So this red here would be the I plane. And X times Z is I times K. Whoops, did I get that off somewhere? What is that? Y, J times K should be I. And I times K, yeah, this will give us the J plane. So there's the three-dimensional vectors that we're used to. So that's what you want to use for your vectors in 3 dimensions instead of X, Y, and Z. Because it gives us a more unique thing. We take a value from this plane, a value from this plane, and a value from this plane, and then our vector just points somewhere out in space. We have an I, J, and K vector, and I'm going to leave a little bit of space to fill in that real part. So we have 3 imaginary parts, or 3 complex parts, since that word's technically not correct, but that's just the one we always learn in America when we're learning this stuff. So we have the 3 imaginary parts, but then we also have a real part, which goes back to the Pythagorean theorem. Right? If we think of some arrow pointing out in space here, just maybe if that's showing like some piece of chalk pointing out in space, we could turn that into a right triangle going back to the origin, just like we did here in 2D-dimensional space. And if we have a right triangle, then our Pythagorean theorem applies, but we're in more dimensions. So instead of just a couple things, we need all those dimensions to add up. Because the I, J, and K values, all 3 of those together tell us what angle the hypotenuse is pointing at. And then from the Pythagorean theorem, a squared plus b squared. And if you have not seen this before, the Pythagorean theorem applies to any dimension. one's obvious, right? A squared equals a squared. 2 dimensions, a squared plus b squared gives us c squared. 3 dimensions, a squared plus b squared plus c squared gives us d squared. So just like up here where I wrote the a's and b's and c's like we first learned the Pythagorean theorem, that's going to get lost in there. Let me grab some colored chalk. You could have wrote the real part squared plus the imaginary part squared gives us the hypotenuse. I'll just write a big H. And we have the same thing here. The I part squared plus the J part squared plus the K part squared gives us sort of the hypotenuse of that triangle, or the length of the vector going off in space. So the magnitude of the vector is what I'm going to write here. So I, J, K, and M for magnitude. So we have 4-dimensional space, but this is our vector pointing off, and this is the length of the vector. So what might help, definitely ran out of room, I'm going to go back and erase some of this 2-dimensional stuff. Hopefully that was review from things you've seen before. So whenever we're dealing with quaternions in game development, I'll just write the X, Y, and Z here. We kind of have a sphere going on, right? That might not, probably not the best drawing, but hopefully you can see how that's a sphere. I'll try to erase the axes inside. There we go. So there's a sphere, little dotted line for the backside. Not a very good sphere. But we could think about anything, rotation in our space as this sphere and a vector pointing to a spot in this sphere. So from the origin, we'll point out to any little surface spot on the sphere, and that's going to be an I, J, K vector. And the magnitude, the real part, as far as what we call it in quaternions, is the radius of that circle. The sphere, radius of the sphere. We're not in a circle now. So hopefully that'll simplify working with quaternions and game development, because instead of a 3-dimensional vector pointing off in space, which there's more than one way to point in any direction when we use just 3-dimensional vectors, if we use a 4-dimensional vector of quaternions, we have one and only one way to think about a point in space. So our I, J, and K, the square root of -1 complex or imaginary part of the vector, is the 3-dimensional angle, a 3-dimensional vector telling us which direction we're pointing in space. And then the real component of it, from when we go back to the Pythagorean theorem and calculate the length of the hypotenuse, if we think about that vector as a right triangle, that real component tells us the radius. So which direction are we pointing? I, J, K, R. So this is a 3-dimensional point, 3D pointing. And this is the length. How far are we going in that direction? And that gives us a unique way to describe any rotation. So hopefully that helps make sense of what quaternions are. So remember your Pythagorean theorem, then your complex parts describe the planes, your numbers in the plane. So we get back to a 3-dimensional vector and the length of that vector stored in one thing. That's what game developers need from quaternions. Hopefully that helped clear that up. And when you're debugging, remember these things. I, J equals K, Ki equals J, jk equals I, and the order matters, so if we multiply in the other order, we get the negative. ji equals negative k, ik equals negative j, and kj equals negative I. Which you might remember from vectors, negative just points the other direction. So that tells us which direction we're pointing in and how far are we pointing to get to a particular spot in space. So that gives us a unique rotation everywhere. Hopefully that helped clarify quaternions. I put this lecture together after it was very confusing last spring in an advanced game development course. So part of this video was to practice the lecture before giving it to my students this fall and again in the spring, so that I have that nice and refined. So hopefully that clarified it, but I have a feeling I'll be doing another take at this. I just wanted to make sure and put that out there because I kept seeing that reference material I've seen before. The quaternions are hard, and it's like they shouldn't be. They should make it easier for game developers. So hopefully that clarified it a little, and you can think of the quaternion this way, and then you don't need to do a bunch of fancy transformations getting back from a regular vector into a quaternion vector.